Well, hello everyone, and welcome back to Adrian's Digital Basement. This is part 4 in the MILMAR Apple II Plus clone repair saga. And almost like deja vu of the last time I worked on an Apple II clone, this is turning into a real long saga. So I have my little piece of paper here with all the things that are wrong with this computer. And on this video, what I'm going to do is I'm going to try to get through everything on this list to get this machine fully operational. And you can see I have a monitor out here because yes, I'm recording this intro after I have already finished the video and I had to break this out to do some final testing. Now, where I left off in the last video, which I recommend you watch before watching this one, is I got the keyboard completely refurbished, but then I went to troubleshoot a problem with the CPU, which I thought it was just getting stuck into reset. And then it turned out that the computer just totally died again. So that means we're starting out part 4 with a dead computer. So basically I've started out part 1, part 2, and part 4 with a dead computer, and the computer died at the end of part 3, which is what I was just talking about. In this video, besides digging into why the computer is dead, I dig into why the colors are so screwed up. And let me tell you, there's a lot of interesting stuff going on this motherboard that, well, caused the colors to look like they did. So grab some popcorn, sit back and relax, and watch me unravel the mysteries of what makes this MILMAR Apple II Plus clone act so strange. And then, well, even at the end of all of this, it's still getting the better of me. So without further ado, let's get right to it. At the end of the last video, I was pretty excited to have the keyboard fully operational and then was kind of devastated that the computer went from working to not working. So let's just set the keyboard aside for now and let's focus on trying to get this motherboard working again. The specific symptom the motherboard was exhibiting was it looked like it was not executing any code. So we didn't have any activity on the RAM. We just had kind of, well, the same thing we had before when we had that bad trace where the CPU was not able to write to the RAM. So it's been a couple days since I worked on this last. Let me get a speaker connected up so we can hear if it beeps or not. And let's see what this thing is doing. What? It's working again? Because I was under the impression that maybe we had a failed chip or another failed trace, but I was bending the board, nothing was really happening, and now it just works? Oh, maybe not. Okay. Well, that's interesting that it worked for a second and then stopped working. And then, do you hear how when I turn off the power supply, we get a little bit of a beep? I wonder if this is somehow related to this power supply connector. Let me manipulate the connector. I'm going to bend it to the side. See, I need to check the voltages. Like, wait, what is going on? You see this, how the picture's coming in and out? Okay, multimeter time. Now, of course, with an old computer like this, we need to have not only 5 volts, but we also need to have plus 12 and minus 5, and that's for the RAM. The RAM will not work properly if you don't have those extra voltage rails. Okay, we got 5 volts, and of course we have ground, so let's go to the RAM chip. I have to go look up what the different pins do on this. So we have minus 5 there, 12 there, and 5 there. So everything looks fine. But then why when I move this do we get kind of beeping out of the speaker a little bit? Plus it's coming in and out as well. And then when I turn off the power supply, we get a little bit of a beep. Like that, like it's trying to boot. Now, the one thing that I did in the last video where I was trying to chase down this problem is I took the CPU out and I sanded down the pins. I think it might be time for me just to try another 6502 in here. It's really just because I want to rule out that we just don't have bad contact in the socket here. So here's a MOS 6502. Let's see what that does. Well, is this just fake? Like it's going to work once and never again? Okay. You're kidding me. You're kidding me, really. I don't want to rule out that the Cinetek CPU is dead or something. It's just the pins look bad. I sanded them in the last video. This seems to be working now, and it just must be bad contact in this socket, which I did deox it last time. So I think I just need to give this CPU a little bit more attention, or at least these pins, and try to get them looking a little bit better than they look here. All right, check this out. That looks a whole lot better, doesn't it? I ended up using one of these green kind of rubbery polishing bits, and that did a good job. Now I hear people saying, oh, you didn't do the inside, but it doesn't matter for these sockets. These only grab the chips on the outside. And you can kind of see that if you just look down there in that socket. Now, of course, I didn't polish the socket itself, but I don't think it matters necessarily because obviously this CPU works in there perfectly. And let's be honest, I should have put 2 and 2 together, that this computer was working fine, and it was only when I tried to address the particular issue that I thought was the reset pin, which was very tarnished on the CPU, that I sanded it, and then it got worse. So it seems like in this case, correlation was actually causation, I think. Well, let's see what happens when I go to turn this computer on now. Here we go. No. Wow. Is the CPU bad? It's quite possible it's failed. I guess it's failed. And the CPU has just packed it in, said I'm done, given up the ghost. We'll give it one more chance. I just gave it a little straighten, the pins that is. And I'm going to put a little deoxide in the socket. Oh, this thing is spraying everywhere. So what happened is I had to refill this. And after you refill this from the deoxide bottle, you need to leave the cap open for a while so that it lets all the propellant out. And unfortunately, well, I did leave it out, but it's still spraying everywhere. Ugh. Oh, so frustrating. Look at this mess. Well, hopefully enough of that deoxide went into there and got on the contacts. So let's see what that did. No, same freaking issue. Unbelievable. I mean, it worked for all that time and then it decided to be done. And it's done. Okay, well, and with the MOS 6502, it comes right to life. Okay, so we know what that means. The Synertech 6502A gets the X of shame. Believe it or not, this is only the second bad chip from the motherboard, so the only other one being the bus transceiver. The EEPROM came from the keyboard, and it's not bad, it just has bad legs and corrosion and stuff, because it was exposed to a lot of harsh environmentals. So 2 bad chips, that's all we've had so far in this motherboard. So here's my little list of things that have been wrong with this thing. So we have a bad AT28, which is fixed, bad trace, which is fixed, and I just added bad CPU to the list, so that is now fixed. And what we're left with, as far as I'm aware, are only 2 other problems, bad color and no color killer. To properly get to the point where I can demonstrate both these problems, let's hook up this floppy drive again and test out the system with some color bars. And of course, I'm going to need a keyboard because all these diagnostic programs require some amount of typing. Luckily, this keyboard is fully operational. Well, it was at least when I finished working on it in the last video. It's booting right up. That's awesome. I think my floppy disk is going bad though. There we go. Apple Silicon 2 by XPS Incorporated. So one of our issues, as I mentioned on my list here, a lack of color killer. That's why we have color fringing on the text right now. But if we go to other tests and we look under CRT, and this low-res graphics color bar test should show all 16 colors. Well, there's actually 15 because there are 2 shades of gray, which are the same. And of course, no Apple II has this many shades of blue, purple, and green available to it. So this is our problem. Now I have one hunch that I think I want to address first. I don't have an accurate frequency counter, but I want to check to see if this master oscillator, which is this crystal here, is actually the right one for the Apple II. The Apple II should have a crystal like this, 14.318180 megahertz. And the reason why that frequency was picked is because if you divide that down properly, you end up with a 3.54 megahertz color carrier that NTSC runs at. Well, I was talking to one of my viewers who lives in Brazil, and they said that the video system that was in use back in the 80s was something called PAL-M. M like movie, not N like Nancy. That particular TV color system was a weird version of PAL that ran at 60 Hertz, and it used a color carrier that was actually much closer to NTSC's. It wasn't exactly the same though, it was just much closer as opposed to the normal 4.43 and 50 Hertz that's used in, well, most of the rest of the world. So what I had read is on a lot of the Brazilian clones, the crystal oscillator that was used was actually not the 14.13 whatever that's normally used in North America. It was actually slightly off, like it was like 14.0 something or other. And that has me wondering if this crystal, which I hadn't really looked at, is one of these slightly off frequency crystals. And it looks like it is. 14.068 megahertz. So perhaps our problem is that this is off and it's some kind of a harmonic of the normal NTSC color carrier, and that might be why we're getting those strange colors. I would think that you wouldn't get any color, but I don't know. I'm also noticing that this seems like it's loose. So I don't know what's going on there. I think the crystal itself is broken because I don't see the legs under here wobbling when I move it. So I think I should swap this out because I think that's just a recipe for potential issues in the future anyways. Not to mention maybe it's that slightly off frequency that's causing our color problem. And yeah, check it out. These legs, they're loose inside the crystal. Oh, that can't be good. The other thing I'm noticing is that I thought it said 14.0689 or 62, but that's an A. It says 1A. Oh wait, no, there it is. It's on the back. I was looking at the wrong thing. It is off though. 14.30244 versus 14.318180. Well, anyways, this thing looks like it's going to fail anyway, so it's best I just swap it out. All right, let's see if that made any difference at all. Okay, so one thing I'm noticing that I think actually looks more correct, the color fringing on the text was going in these diagonal lines, at least to some extent. And now it all just looks perfectly, lined up, which is how it should look. I don't know, I shouldn't get ahead of myself. Let's just go to the color bars and see if that made any difference. Maybe it's not gonna have made any difference, I don't know. Oh, it fixed it. That was it. Well, now the hue is way off because the color trim needs to be fixed. Well, today I learned that if you use the crystal that's from the Brazilian market here in NTSC land, you do get color. It's just the colors are all wrong. Wow, let's adjust the color hue. I think it's off a little bit. Seems like I can't adjust this correctly, actually, the color trim control. So the colors are wrong. Okay, so what we might be having a problem with now is actually that extra line that's over on the left side that's really screwing with the retro tank. Although, I don't know. I'm thinking one of the issues here is that there are some other values of capacitors that are on here that are affecting the artifact color, maybe to make this more suitable also to the Brazilian TV standard, which keep me from using the color trim, which is an adjustable capacitor, to dial it in correctly. Like the entire range of this capacitor might be affected by another capacitor or two that's right near it. Now in part 2, when I load up Fat City, which is of course my test game that I always use on the Apple II, it plays music, it has color, graphics and whatnot. I noticed that the sound was weird, and I guess that makes sense that the master oscillator was different because of course that determines the speed of everything on the computer, including the CPU. And I guess what I was hearing was just the frequency was slightly off. So let's put this in and let's see how the graphics look now. I don't know, the sound's still weird to me, but maybe that's just the speaker. And yeah, the color's completely off. Like the sky should be blue, not green. Well, if you've been keeping up with this video series, you know that I've been using the Apple II circuit description by Winston D. Gaylor for all of my schematics need for Apple IIs. Unfortunately, the original Apple II schematics are incredibly hard to follow, so you really do have to use a book like this to try to understand how the system and the circuits are laid out. Now, this is a clone, which of course means there are some subtle changes on here, but I think for the most part, this is a carbon copy. So we can totally reference this document. Now, here is the actual crystal that I replaced and the oscillator circuit around it that generates the 14 megahertz, and then that feeds into B1. And notice this generates a bunch of different things, including the color reference signal. That is absolutely going to be the color burst, and that totally determines how the colors are going to be rendered with NTSC artifact color. Now, I'm not suspecting that this chip is a problem by any means, although, I don't know, it should be an S175. That chip right here, it's a 74S175, so they used the correct part. I was just wondering if it maybe was a slower part. The propagation delay would cause a phase shift in the color reference, and any kind of a phase shift you have between the luma pixels and the color carrier are going to alter the tints. And that's what I am suspecting with this color trim pot, that there's probably some other capacitors around it. Like it says this should be a 50 picofarad adjustable cap. Well, maybe there's some other caps that are near it and they've substituted the values based on what should be there, and that has affected the tint of the entire picture where I can't dial it in properly. All right, so this is the video generation circuit. There's the composite video output. Color reference comes in. That's what we saw on the other page. Goes through these two gates. It goes through an inductor and then a capacitor 47 PF. And then it has that hue adjust. That's the control I was trying to adjust and didn't seem to be doing anything. Now I can see the 47 PF. Well, it's marked that way on the board. Where's this inductor? 27 UH. Okay, there it is. It's actually 22 on this board. I don't think that will have an effect of ruining the color specifically. I think the capacitors have a bigger effect on the hue. Anyways, the color burst makes its way into the mixing circuit, so 2.7K, 1.5K, and a 2K, and then that gets buffered before it makes its way through the video level control, another resistor, and then out the composite video jack. I think what I should do is I should check the values of these resistors that are down here on the edge of the board, just to make sure that they actually match what's on the board here. This says 15K, but I think it's actually 1.5. Okay, that is correct. That's the video signal itself. And then this resistor is 900 ohms. Well, none of the ones listed on the schematic are 900 ohms. Okay, so this is 2.7K, and this absolutely is for the color burst. And we can tell because this side of it should make its way to the cap, the adjustment, the hue adjustment, and it does. Okay, so 2.7K is correct. And then this one is the one that's wrong. This is the one that's used specifically, the middle one of these three. That one is used for sync. And then the video data one itself is this one, 1.5. So this is the actual serialized display data itself. So that is correct. So I should swap out this 900 ohm one for 2K-ish, something like that. That might fix that weird bar we have on the left side that's kind of messing with the entire video signal as well. Okay, so I know that one needs to be replaced. Let me get a marker so I can mark it, just so I can remember that this one I got to take out and swap. So the middle one. Now the little 47 picofarad cap that has to do with the color hue adjustment is this one. It's so small I'm going to have to kind of tilt the board to try to read it. Well, whatever marking was on there is completely unreadable even with the loop. And then I guess our question is the little hue adjustment. This thing also should be from 5 to 50 picofarads. And I'm not sure if I can use something like this to properly measure that or this other little thing, especially in circuit. I might have to take both of those out just to kind of check what they actually are. This is saying like, 1,000 microfarad or whatever. So it's probably measuring from the power supply. I think I got to remove these components from the board just so I can accurately measure them. Okay, I've taken out that little ceramic capacitor. That's supposed to be 47 picofarad. I think this little thing can measure something like this, maybe? No, it can't. Okay, let's try something else. How about this meter if I stick it into the slots directly? Inductance? That's, oh, there we go. 42 or 43 picofarads. Well, that's pretty darn close, isn't it? Maybe what I'm going to have to do is just try a few different values in the holes that are in the board and see if that makes the color work better. Now, as for the resistor, that's the wrong value. Let's pop this out and we can check that just to see if it really is the wrong value. That is wrong. It's 900 ohms, well, 890. So unfortunately, I don't have the right 2K resistor, so I have a 2.2 and a 22. So you put these in parallel and that should be 2. And there we go. I'm holding them in with my fingers. That might affect it a little bit, but 1.94K, a lot better. All right, let's see what that did to our video. Hopefully that fixed that bar that's over on the left side and maybe changed the color as well. Maybe. I mean, the 47 picofarad cap's not even in the board. I still see that bar, so I don't know if that's a good thing or not. Well, one thing I noticed immediately is that the overall picture brightness levels all look a lot better. And that's because, of course, things like the RetroTink uses the sync signal to help auto gain the entire image. Now let's just hold this little capacitor onto this and see what this does to the color. Okay, so it shifts it, but not appropriately. So I went and grabbed some little small caps. Let's start holding some of these against this and see what this does to the color. I think this one is 15 and it like literally does very little. So I think to fix this, I have the 47 in there. This trim capacitors from 5 to 50. So that means a total of almost 100 picofarads. So these little 15s aren't really going to do very much. And has me wondering if this little trimmer is not up to 50 picofarads. So that might be part of our problem. And I don't really have anything appropriate in my little bin here. So I'm going to have to go to my scrap boards and start pulling disc capacitors off of there. Maybe I can find a 50 picofarad and parallel it up with this 47 or 43 or whatever this is, and that'll get us a lot closer. Scrap board for the win, a 68, 56, and a 33. I think with these three, we should hopefully be able to dial this in. So you know the drill. There, look at that. I just held the first one on, and there it looks right now. That is awesome. Which value is this? I just held the 33 picofarad one onto there. I'll just parallel them up maybe, or you know what? I should just try one of these other ones. So I could just put the 68 in there, just see what that does. Better, but not perfect. What if I dial it in with this little trimmer? Oh, hey, that's pretty good right there. Maybe. I think it was still better with this original 47 combined with the 33. That gave what I think is perfect color. So I'm going to install them just in parallel with each other, and then we'll dial it up and bring back the color bars and see how the color looks then. The two little caps are paralleled with each other. That should do the trick. It's additive when you do that. Okay, here we go. Let's see what happens. Obviously, the video level's probably a little too high. Well, we can adjust that in a second. Once Fat City boots up, see how this looks. Oh, yes. Yeah, definitely the video level's too hot. Turn this down a little bit. Wrong way. There we go. Yeah, those colors look good. Really good. Let's see. There should be a little bit of adjustment in here. Yeah, that's about it. Got to say, there's a lot of interference, isn't there? And I really think this is the power supply doing it. I just think it probably does need a little bit of recapping on the output side. All right, there's our very noisy color bar pattern. This looks way better. Yellow, oh, aqua. That doesn't look super good. And I can't really dial it in. So the problem colors are magenta should be more reddish, and then aqua should be a little bit more blue. Part of this might be the RetroTink, just the way it's adjusted. And I mean, let's be honest, this is NTSC artifact, never the same color twice. 100% applies to the way Apple II color looks. It's one of the reasons why when you look at the Apple II GS, even the way the RGB colors look on there, they don't even really match the way an Apple II renders it, at least in my opinion. And that's because there really is no standard color, because everything can be a little bit mixed up because of the NTSC-ness of it all. Let me try turning the, oh wow, look at that noise. It's so noisy. We're gonna need to adjust the video level using the oscilloscope to get that dialed in correctly. Part of it makes me wonder if I should grab another little cap and just hold it up there, and let's see what that does exactly. Let's see, I'm gonna hold a 15 picofarad cap up to our little sandwich of caps here. Okay, so I'm holding up a 22 picofarad. It's making the color go out all together. Yeah, I don't really get what's going on there. I think what might be happening is because this is the color burst, which is a sine wave that's applied to the video signal on each horizontal scan line. And maybe when I put too much capacitance there, it smooths it out so much that the amplitude kind of goes away, because obviously it's a changing signal. And if we're putting on too much filtering on it, maybe it makes it where the decoder, the color decoder on the RetroTink can't see it anymore. Now, one thing about this video signal that we're looking at here is the color saturation is so extreme right now. It's really, really saturated, which I don't think is the way it really normally looks on an Apple II. Or rather, it doesn't look the way it should look on an Apple II. And I'm wondering if, what if the color burst that's going into this 2.7 is too low? Maybe this 1K is too hot, or you know, one thing that's a problem is this inductor, 27 microhenries, is a 22 on this board. And what if making that smaller makes the color saturation get more intense? I think we need to scope the video signal and just take a look at how things look, because there's something still going wrong in this whole mixing circuit, I think. First thing we're gonna look at is the video signal, and I can tell the level is way too low. It should be, I mean, just the active video signal part of it, which is this section right here. If we stop this stuff here should be about 700 millivolts peak to peak. And this is where it really helps to turn on the cursors, and we can use this to help us dial it in. Now what we need to do is start this. Okay, so there is our video signal, and I'm going to need to turn up the amplitude till it starts to look correct. So what we're going to be looking for is from the bottom to the top, we want it to be about 700 millivolts, which, yeah, okay, that's about that right there, actually. There's our color burst. You can just sort of see it there. And there was that little extra spurious line. Now, since I changed the resistors for the sync mix, which was, where was that? That was here, R8. I put a 2K there. That actually lowered the amplitude of both of these. Now, this spurious little thing there, it shouldn't even be there. Now, where is that coming from exactly? Well, we can check by looking at these resistors. So first we're going to look at this one, which should be the video data. Of course, it's going to be way too hot. So that's our video data. That's the actual pixels themselves, no color information. Then we have this one, which is the sync information. Oh, there it is. There's our spurious little thing. That shouldn't be there. That should not be there. And then this one here is the color burst itself. And there we go. And there it is. Now it looks pretty low amplitude right here. And I don't remember the relationship of this particular signal when it comes to amplitude versus how saturated the colors are. But I have a feeling because I had the video gain turned way too low, that was causing the RetroTink to cause the saturation to be really too much. In fact, yeah, that seems maybe a little bit better. It's really hard to tell though, isn't it? Let's switch to component mode. Now things are looking too blown out again. That is because of this extra spurious black line that's right there. It's causing the auto gain control on the RetroTink to, well, to think that the black, which is the background, is actually brighter because it's actually using that little pulse that goes down as the overall reference for the entire image when it comes to the automatic gain control. I don't know if that would necessarily be affecting a CRT the same way, but it's definitely affecting the RetroTink, at least in this mode. In color mode, it doesn't happen as much because it applies a low pass filter, and that's a pretty high resolution little thing there, much smaller than a pixel. Look at the BLK down there. See how the width of the B is quite a bit wider than that little thin black line? So it kind of ignores it in color mode, but in this mode it doesn't. So when we adjust the tint, or we add the little capacitors on here to adjust the tint, what it's doing is it's altering the phase of that color burst. So those vertical lines are tricking the color decoder in your CRT or the RetroTink to produce a color. But when you're moving those pixels you're seeing there, or the color burst side to side, you're adjusting the phase of them, that's what changes the tint, which is the hue of the entire image. And from my recollection, the intensity of the color, the saturation of the color, is how intense the white and black lines are in these vertical columns. That's what's tricking the color decoder. If those are less distinct, like say it's just a solid gray or solid white or solid black, you don't get any color. But then the higher difference in luminance between those black and white stripes, those vertical columns, that's how the intensity is controlled. Don't think it has anything to do with the amplitude of this color burst. I don't think, at least. Now we're looking at the base drive of Q3, this output transistor, so you get a clearer image of what the video signal looks. So you can really see these up and down lines, if we pause it right there. So what controls the hue of the image is the phase of these spiky parts here in reference to this color burst. That color burst just looks too low. And I think that's why when I was adding that capacitor, it was causing the color to disappear altogether, because I think I was just sort of taking out too much of the amplitude, smoothing this too much. I almost feel like I might need to add an extra resistor on top of R6 to increase the amplitude. This just doesn't look like enough of a color burst. It should be more. Let me try holding this 10K resistor on top of R5, and let's see what that does to the amplitude. Nothing I can really see. Let's see if this resistor is R5, this 1K resistor right here. Let me see if that actually has like 5 volts on one side. Yes, it does, kind of. I don't... This is the output of a gate, and it looks like this? I don't even understand. What we should be looking at here on this R5 is pin 12 on this gate, and that does not look appropriate. Like, this should be 5 volts peak to peak, and that is definitely not 5 volts peak to peak. All right, so that chip that's generating the color burst, which I have the mouse pointer over right here, B12. If we look at pin 12, there is our signal. So the amplitude is not very high. I'm wondering if this chip just doesn't have a lot of drive strength. Let's check on the pin of the chip itself. No, it's the same. So the socket's not bad. Okay, wait a second. This is weird. I don't get this. Now I'm on this side of the 1K resistor R5, and look at the low amplitude, 2 point something volts. But when I go back to the chip, it's stronger. So what's happening between there and this resistor? You can ignore that. Don't worry about that waviness. That's my probe having issues. So one side of the resistor, which I think the side I'm on right now faces the chip, but the other side should be even lower amplitude. Yeah, the other side of the resistor, it's like super low amplitude. Well, this might be a nothing burger, what I'm chasing, but I just want to see why the amplitude is so low when we get over to this resistor. Okay, wait a second. This doesn't make sense. Unless this resistor is not, well, no, I'm pretty sure this resistor is the one that goes to the color mixing circuit over here. Yes, it absolutely is, because one side of it, we saw that less than an ohm. Let's measure it while we're at it. Should be 1K. It's not 1K. It's 500 ohms, even though it says 1K on the board right there. But then the question is, this should be connected directly to this chip right here, and it's not. That kind of implies there's a capacitor in between this and that. These are the mysteries, everyone, of these clone boards. They make changes to stuff. They don't even mark it on the PCB, and I don't know what's going on. And in case you're wondering, if we look at the different revisions of these boards, revision 0, that's pin 12, that goes to there. This is the next revision, same thing, no change. This looks like there's possibly an extra little thing here. That's optional, but anyways, that doesn't affect what we're looking at. Same thing there, and same thing there. And that's the RFI, the last revision of this motherboard. But that implies either we have a bad trace. That's possible, I suppose. Oh, I mean, it's totally possible, isn't it? I think our other bad trace was literally in this area. Wait a second, was it on that chip, actually? Don't tell me it was on that chip. Let's look. No, it wasn't. It was on that chip there, which is a different row altogether. Well, I guess what I can do is I could just temporarily at least put a bodge wire from that chip right to this resistor. Actually, before we do that, let me just use clips, and that way we make sure that this actually has any effect anyways. I just don't get it. Why are we getting mega ohm, and yet I am seeing that signal? The color burst is there, but is it just inductive or capacitively coupled or something like that? I mean, is it me, or is this actually a little bit better? Let's unplug this clip. It seems like with this connected, it's just clearer and better. The colors are more accurate. This is how it really should look. The magenta is kind of a purplish. That's how it always is. So my question is, when I unplug this clip lead, where's the signal coming from at that point? I don't quite get it. But I suppose one thing we know should be the case is that it should be connected, and it definitely, the video signal looks better when it is connected. So I think I'm going to bodge it. Okay, well, I was about to bodge that connection, and I actually have a little wire attached just to the chip. But then I started looking from the resistor, that's the resistor right here, and I started tracing it. It makes its way over to this part of the board, which has these extra chips on here, which I don't think the Apple IIs have. So this is something that was sort of added after the fact. And this one, which I think is what's actually going to that resistor, is a 4066, which is a switch, I think. So we're in continuity mode. One of the probes is on the resistor, the side that faces I thought faced this chip right here. But let's see. Oh, there it is. So the signal that comes out of this, the color reference, or the burst that is, there it is. It goes to this little switch here. But I also noticed that that color reference signal that comes out of here, I think it goes to these little capacitors as well. At least one of them is in circuit here. Now I think if I just take this chip out altogether, we'll see what that breaks on the computer, but I think that might just break the color unless it's being used for other things. I mean, you can kind of make out that these traces, like notice how all the other traces are nice and smooth and squiggly, but these ones don't look so squiggly. It's like this was all added after the fact. Although I could see something that this chip is connected to this other chip that's there. So potentially these are both doing stuff around color. I'm curious with this chip out of the board, will this machine even work now? it does work. We do seem to still have color, which is really surprising to me, again, because I thought that chip was part of the color circuit. Uh-oh, I think we're back to not working. I plugged the disk drive controller in because I wanted to boot Fat City. Let's see what it does without this. No way. We're back to not working? No, no. Oh boy, this motherboard is really trying my patience. So this bodge wire, by the way, is not attached, and I'll remove it since it's obviously not the right solution for this problem anyways. I'm just manipulating the chips that are in the board here in the sockets a little bit, kind of sliding them around. Did that make a difference? That made a difference. I mean, which one was it? I don't know. I moved a whole bunch of the chips. Wow, this computer. The whole thing is so weird to me. And the color looks absolutely horrid now. Well, I'm kind of curious what this chip next to it does because it's also seemingly related. So what about now? Computer still works, and yet there's still color as well. How is there color? How? So the color burst output is found on 2 pins on the 4066 socket. You know what? I'm thinking that this is actually a way to get color on PAL from an Apple II, which maybe somehow, I mean, I don't know, we're not seeing it though, but I mean, maybe it's trying to like switch the hue back and forth, that somehow would make color work in Brazil. If anyone watching this is from Brazil and had one of these computers, maybe not this exact one, but one of these Apple IIs, did it have color on the TVs in Brazil without needing an extra card? Because I did some reading, it seemed that some of these machines came with a card that had a PAL encoder, so it would convert the Apple II graphics to PAL compatible. But I'm wondering if these two chips are trying to do the same thing. And that's why there are those extra capacitors over here, is maybe it's trying to alternate the hue. Because of course, if the color burst potentially alternates 180 degrees per scan line, that's what PAL is phase alternating line. So all the color information is flipped every other line, and that's what allows you to not have any kind of a hue shift when the signal changes and stuff like that. And I'm wondering if these are doing that, because obviously taking them out doesn't have any effect on the system. And if we go from the resistor for the mixer, there are these extra capacitors over here. Are any of these hooked up? Let's see what is hooked up. Yeah, that one is hooked up. Don't know what it's hooked up to. No, I can't really quite figure it out, but I really feel that like this little circuit that they built here was to try to make color on an Apple II in the Brazilian TV system. And that's why taking these out seemed to have like no effect. And really, if I just add the bodge wire now from the output of this to the resistor, that bypasses this stuff anyways, because I just removed those chips, that I think that should make the NTSC color work properly. And interesting, if we switch this back to resistance mode, and now we take a look from this pin over to the resistor, I don't think we're going to have the 5 megohm. Yeah, it's just open. It was 5 megohm because it had those chips in place and it was going through those chips. Another thing I'm noticing is that the output of this chip, which does go to a capacitor right here, and this is what makes its way to that resistor for the color burst. It goes to a resistor, which is that one, and then it's going to this capacitor. So there's definitely stuff in circuit that's still happening here. And that must be how the color signal is still kind of making its way through. So I just need to remove those components because none of that stuff is needed for NTSC color. And once I've removed those, then all I need to do is add a little bodge wire that goes from that pin to that pin and leave that chip out. And that'll connect that LS12, the output of that, the color burst, over to the video mixing circuit. All right, here's what I did. I ended up moving both of these capacitors. This was the one that was over on the left side, and then the one on the right was this one here. I should measure these, try to measure them, and then write down their values. This resistor was in place. See right where it says speaker or SP? That resistor was there as well. I had to remove these because it looked like those other resistors were in play as well. And I think that's how we had color information getting through even with these chips removed, because those resistors were hooking that stuff up. It's all bypassed now though. I actually think I might have to take this bodged capacitor off because that was trying to make up for all the stuff that was going on over here in this section. Also, let's hope that this thing actually works and me handling the board didn't make it break again. No, it broke. It broke again. You're kidding me. Come on. There it is. This thing is still touchy. Very touchy. Just ignore that it's all bright. By the way, that's just the retro tank. Let's see, this is Fat City loading. Okay, yeah, it looks good. First of all, this hue control over here doesn't seem to do anything. Right now, the color's stable at least. So I just adjusted that a little bit. I do wonder if I should remove this extra little cap, but it feels like this value, which should be 50 to 5 picofarads, is not that. That's not what this trimmer is. Don't know if this trimmer like does nothing, to be honest. In case anyone's wondering what the values of these components are that I removed from this extra little circuit, it was a 38 picofarad, 42 picofarad, and a 1K resistor. And then the two chips were an LS86 and a 4066. I didn't really work out exactly how these are all hooked up, but I put pictures of the motherboard on my GitHub. So if you want to see close-up pictures, you can make out some of those traces, at least on those high-res photos. So back to our little list of problems, I've added a few of the things that I forgot to add, like interference in the video and random no start, plus the vertical line on sync, which is better now that I've changed out that sync mixing resistor. And of course, we have no color killer. I was able to cross out bad color since the color looks like it's working well now. Now going to my little bad parts bin, I accused the original CPU of being bad, but I actually think that it might not be. And this has to do with the random no start that I'm getting on this machine. The idea that this CPU might not actually be bad stems from a comment on part 2 in this series from patron and friend of the channel, Bradley Bell. Brad is an expert in Apple IIs and has reverse engineered a whole bunch of Apple II cards. I'll link to Brad's GitHub repo if you want to check out those open source recreations of all those Apple cards. Well, it was in part 2 where I figured out that there was a bad trace that was connecting Phi 2 or Phi 1 from the CPU to one of these chips. I can't remember which one it is. And that signal from the gate went to the bus transceivers that hook the data lines up to the rest of the system. And the side effect when that trace was bad was that the RAM couldn't be written to. It could be read from, but not written to. Well, not just the RAM, actually anything on the board. This was the fix that I applied, thinking that these two inputs on this particular gate were both Phi 1, and I could just join them together to actually make the system work. And when I installed this, it seemed that the system did work. Looking at the circuit description, we have Phi 1 output from the CPU goes into this gate at C14. It is gated to the read-write signal, also comes out of the CPU, and then that pin 8 makes its way over to the bus transceivers. Well, actually, this is the wrong one. It's this one here. These are the bus transceivers 8T28s, and this turns on the reverse direction as necessary so that the CPU can actually write to the RAM or any other peripheral on the system data bus. The particular problem I identified was that pin 3 did not make its way to pin 10 all the time. It was an intermittent connection. It was a bad trace on this board. And I made the incorrect assumption by not reading properly that pin 10 on C14, the Phi 1 input into that gate, happened to be exactly the same as the Phi 1 input into pin 12 on that same exact chip. So that little bodge wire you saw me put on the underside of the board was just connecting pin 12 to pin 10. Notice it says Phi 1 as well. Well, the key part here is that this Phi 1 is not the same Phi 1 that comes from the CPU, and it says from clock generator. And if we look at the page for the clock generators, we can see that that is indeed the case. There's Phi 1. It actually comes from the 74S175, which is responsible for taking that 14.31 megahertz crystal that we worked on earlier in this video and dividing it down to create essentially a Phi 1 signal that's very similar to the Phi 1 on the CPU, but obviously not exactly the same. And the funny thing is, when I installed this bodge, the system generally seemed to work properly. So the Phi 1 that's generated by the clock generator seems to be compatible with driving these bus transceivers and turning them into the other direction so that the writes to the RAM can work. Well, what Brad pointed out, and he was totally right, is because those two signals, those Phi 1s that come from two different places, are two different outputs. Well, you shouldn't really ever just connect two outputs together directly like that. That's just bad to do. And while my little bodge seemed to make the system work, I'm wondering if all the weird instability with this machine where it doesn't always turn on, which we've been witnessing, well, once I fix the keyboard in part 3 and then, randomly in this video, is all due to the fact that, well, I'm taking the signal from the wrong Phi 1, so there's that, but also the fact that maybe intermittently that bad trace is getting reconnected and it's connecting those output drivers together, and that's causing, well, it's causing weird things to happen. So I think what I really need to do is I need to remove this little jumper link that I've installed, And then I obviously need to add a proper bodge wire that goes from pin 3 on the CPU, Phi 1, into pin 10 on C14, and then hopefully that corrects the instability issues. And my thinking is that this original CPU will maybe start to work again. Now I've gone ahead and I removed that bodge from this chip, and this is what's funny. Pin 3 on the CPU is actually connected right now to this chip, pin 10. Well, my problem is now is I still believe the intermittent trace problem is still there, which is why the system works and doesn't work sometimes. And I don't know where the break is, because it looks like pin 10 makes its way to this via, and it looks like pin 3 on the CPU makes its way over here to one of these vias, that one right there. And I wouldn't be surprised on the top side of the board, that via is then connected to this via. There's probably a trace there. And we could have a problem with any of these traces connecting to any of these vias, or like this trace connecting to that pin, or this trace connecting to that pin. Well, I've already reflowed that since I put that little metal bodge wire on there, and maybe that was all it took to fix that particular trace. So I guess to really be sure that this is not going to have another issue is I should just add a bodge wire directly from the CPU to there, just so I don't ever potentially have a problem in the future. Okay, it's a little bit hard to see, but I've done the bodge. It's in a green wire. I'll glue it down later once I make sure that this is actually working properly. All right, let's first test with the MOS CPU in here. Came right up. Well, I thought it came up correctly, but I'm just noticing it's opal, and we got some bad characters there. Well, it worked that time. Well, that's not reassuring, is it? With the original Cinertech CPU back in there, let's see if this thing works now. It does. So that was the It does not. Okay, how interesting. All right, well, there we go. That weird problem with that beeping and stuff, whether like it was getting stuck kind of resetting multiple times. Clearly that's a problem with this CPU, and it is actually bad. Is it possible that I damaged the Phi 1 output because I had it shorted to something else? Yes, entirely possible. But actually, I don't think that's a damaged output. I just removed the LS32. Let's see what it looks like without any kind of load on it. It looks basically the same. I don't quite remember what this signal looked like before I joined it to pin 12 on the little chip with that bodge, but this is coming from the CPU, and then the one I joined it to, well, it looks like this. Well, here's pin 10 and 12 together on the oscilloscope using the two channels, and they are slightly out of phase. That means that they were actually fighting against each other ever so slightly, and possibly that damaged the CPU's output and it made it more curvy there. That's the red trace. And this is the MOS CPU, the one that's been working. And actually those signals look pretty much exactly the same amount of out of phaseness, the same curvature on the rising edge of the CPU's Phi 1. All right, so I don't think that's necessarily why the Cinertech CPU was freaking out. So I think that pretty much concludes the Phi 1 output on the Cinertech CPU is not bad, it's not damaged, and this CPU just doesn't work properly anymore. And the MOS one that's in there seems to work a whole lot better. And if I put back in the LS32, there we go, we have a working system. I still don't know why that first time I powered it up though, oh, I just touched it and it did that. I wonder if this machine is just gonna plague me with gremlins forever. And it has me thinking now that this random no start condition this thing has been having has nothing to do with the correction of the Phi 1 stuff I just applied. I wonder if this thing is still just gonna act up and, well, not start sometimes. Seems to be working now, at least, for the most part. Okay, so for random no start, I'm just gonna put a question mark here to tell us that I think I fixed it, but maybe I didn't fix it. The next thing I want to work on is no color killer. This is causing that color fringing on all the text in text mode, which should not be there. So if we look at the color killer circuit, there are two versions that are on the Apple II. Now, there's this version, which is what, revision 7 of the motherboard? And there's this extra little circuit here with these two gates at A14. And A14 is in the section of the board that I just removed those two extra chips from that I think had to do with the PAL color circuit on this machine. It looks like Apple added an extra 74LS02 that actually just shuts off the color reference circuit when text mode is engaged. I think that's what's happening, because notice this little section is in that little box there. This top line is the text mode signal, and it goes into this gate, pin 6, and the color reference signal goes through B13, and then it goes through this A14 gate, and then through the second gate, and that pretty much has the effect of disabling the color burst entirely at this point, when you're in text mode. But Apple had already added this color killer transistor that also shorts the output of the color burst directly to ground whenever text mode is engaged. Well, I don't know why they added this extra little circuit here. Maybe they found that the original color killer, which was this one, leaked or something, like it allowed the color to come through even when it should have been disabled. So they added an extra chip to disable it. But then the weird thing is, if we go down to revision RFI, the very last revision of the Apple II, they actually removed that and they went back to just using the same transistor. I'm actually realizing that they did keep that chip on the later RFI version, A14. That's that same section in the bottom corner here. So there is that extra gate there. And I guess what that does is it does turn off the color reference entirely to the circuit. Interesting. Well, it looks like we have the Rev 7 circuit on this board if we ignore the extra A14 stuff. Well, the text mode signal, which we have to go find on this text mode page, we have to find that signal. So we have to make sure that trace is good. That goes to R27, the base drive for Q6. There's the text mode signal, pin 4. And we looked at this chip before because we actually had bad contact. I think this was in part 1, or maybe it was part 2 where we looked at this. This chip, F14, there was something wrong with it. Remember, it was always showing page 2, and it had just dirty contact in the socket. The chip itself is a little bit tarnished, but not that bad. Well, this is the chip. There's the resistor, 4.7K, and this is the color killer. And we should be able to go from there to this side of the resistor. And we do. We have less than an ohm. So that seems like it's a good connection. And this resistor here, R27, let's check the value of it. This is what goes to the base drive. 1K. Why do they just randomly change their values? They just had these resistors lying around and just shoved it in there. Let's check to see if this transistor looks okay. So base to emitter, it's 0.7. Base to collector, 0.7. So the transistor looks like it's working as well. So looking at the output of this chip, pin 4, this is the text page. Currently, it is up at 3 volts. Now, when I turn on the system, I'm going to turn it off and turn it back on. It should be in graphics mode for a second. It is, and then it goes up high. Now, when we take a look at the output of this base drive resistor, 1K, see, I don't know, it's at like 600 millivolts. Is that the correct value to turn on this transistor? All right, so let's take a look at the various mixing signals that are these resistors right here. So this is the video data. So that's the little Apple II we're seeing on the top of the screen right now. And then this one should be sync. So these are our sync pulses, including that little spurious pulse, which we'll have to take a look at in a second. And then this resistor here is the color signal, this one. And I don't see any color burst right now. But obviously we have color because there's color fringing. I plugged in the floppy drive controller so we can boot this thing up and get into a game. So we booted up Fat City. It is in graphics mode right now. So we take a look at pin 4, which is the text mode output on the chip that feeds into the color killer, among other things. The signal is low now, which is correct. When we were in text mode, we saw this up around 3 volts. Let me take the disk out. So if we turn the system back off and on, we're going to be in text mode. So if we take a look at R6, 2.7K, which is this one, we don't see a color burst. And we look at the other side, which is the mixed video signal, and we just see a black screen right now with no color burst. So why is the RetroTink enabling color decoding when there isn't any? I don't get it. If I put the disk back in, as it starts to load, there's the color burst as I switch to graphics mode. So the color killer circuit's working correctly on this computer, but for some reason the RetroTink is decoding. There's the graphics right now of Fat City. For some reason, the RetroTink is enabling color decoding all the time, even though the color burst is definitely not there in text mode. And part of me wonders if Apple added this additional little circuit here with A14 on the later revisions for this exact problem, like some tiny amount of leakage of the color burst that makes its way through. Maybe somehow that allows the color circuitry decoding to still be triggered, even though it should be turned off. Okay, I think I'm on a wild goose chase. As you can see, we're booted up. The colors look wrong, but they're there. And what I ended up doing is I removed the little bodge wire that I installed on the socket where this 4066 chip was. The bodge wire on that socket was just passing through the color reference, color burst signal all the way through to the mixing circuit. So with the bodge removed from the bottom and this chip not installed, we don't have a color burst making its way through to the video output.
So why do we have color? I don't know. But if I install the 4066 right now, this chip is going to act as a pass-through for the color burst. And you should be able to see the color is going to look correct right now. There it is, looking perfect. Now, 3 and 4 are the color bursts going in and out of this chip, and pin 5 is the actual switch. Basically, this switches the chip on and off. So if I give it 5 volts, well, we get the color burst and the color looking correct. And if I give it ground, it's essentially turning off the color burst right now. So this should be removing color entirely from the video. And my assumption is if I hook up a CRT, it would. And if I turn it back on with 5 volts, there we go. Now the color looks correct. It's being passed through correctly. And if I hook up the oscilloscope, believe me, the color burst is going to be there right now, which creates the correct colors. And if I give this thing ground for that switch input, then we don't have a color burst. It disappears. So I think what's going on here is the RetroTink is just somehow decoding color when it shouldn't. Maybe it has to do with the fact that the video signal is noisy and that's tricking it into thinking there's a color burst, or maybe it's that vertical line on the sync signal that's thinking it's a color burst somehow. Now, the reason why I put this 4066 back in here is I was just going to wire this up to the text signal using a baud wire and just allow this to replicate that circuit that Apple had that absolutely turns off the color carrier entirely when you're in text mode. Effectively, I was just going to replicate what they had here, except I was going to do it in a little bit different way. Instead of turning off the color reference entirely, I was actually going to interrupt the color burst itself with that 4066. I was just going to use the text mode line to be controlling that switch on and off. But manually switching it on and off doesn't actually work with the RetroTink, so I don't know if there's even a reason why I would want to leave this in. Now, I suppose that brings me to the sync issue that we have with that additional spurious pulse. I have seen that sync pulse before on other older Apple IIs. All right, so if we turn on the system here, there's that spurious pulse. All right, so this is 9, 10, 11, pin 12 doesn't have anything coming in right now. Pin 13 also has nothing coming in right now, and pin 1 is right there. So my assumption is this is happening because one of the inputs has a little bit of propagation delay or something on it that is just causing a little bit of overlap, and it causes that extra little output. So I've gone ahead and I clipped onto that chip so we can look with the other probe at the various inputs and see how they relate to the output. Okay, so here's pin 9, and you can see pin 9 is falling, and it, I think, is responsible for this. Let's look at the other ones in relation. Okay. And also this one, which is pin 10, is going high. So I think it's probably 9 and 10 falling, and there's a little bit of a gap there potentially. Let's look at 11. Oh, 11 is also doing it. Over here on this gate, 12 and 13, I think, are unrelated. Yeah, they are. And so is pin 1. There's pin 1. So it really is this 9, 10, 11 that's causing that extra pulse. So in order to fix this, I feel like we have to add some additional propagation delay to one of these signals. So that's pin 9. Maybe like this one needs to come sooner. I mean, ideally, just trying to think here. I wonder if just swapping out some of these chips with like slightly different ones might change things. Like a different LS51. Maybe it'll just behave slightly different. This one is a national semiconductor part. Looks like 11 goes to, looks like pin 10 actually is driven by a transistor Q7. I wonder if this is something to do with propagation delay. And maybe they added these values to kind of slow down the transition. I mean, there's no capacitor on here, so I couldn't say for sure. I'm not even sure where this transistor Q7 actually is on the board. We're looking at the revision 7 version of the schematic. What about the other revisions? Oh, they don't have that. Okay, so maybe that is exactly for that reason. In fact, 10 and 11 are hooked up to the same signal on the earlier revision, H3. But we could see that on this later revision, it's H2 with that transistor, and then the other one is hooked up to H3. Actually, now I think about it, this might be inverting this signal. We'll be able to tell how this is hooked up if I just take a look at 10 and 11 with the multimeter, and we'll see if those are actually shorted together. Yeah, they are shorted together. So that means they replicated the earlier version of the board here, where H3 drives both of those. I'm noticing the one with the transistor, if you look at the RFI version of the board, there's RFI, it's using one of the extra gates down in A14 area on the 74 LSO2, also used for the color killer circuit. And my assumption is this is adding that propagation delay to actually get rid of that extra line. Oh yeah, and by the way, this is a NOR gate, which means it inverts this signal. H2 will go into this and then get inverted on the output. So low, low equals high, or high, high equals low. So I think that means that there's no fixing that vertical line, not without rework, because I'd have to repurpose one of those empty sockets in the corner there to be an LSO2. But the bigger problem is those two pins that go to the LS51, they're just probably shorted together right on the motherboard. I'd have to cut them and then run a bodge wire over to the LSO2 and then hook up that LSO2 that I add to A14, hook it up to, well, just replicate the way it is basically on that RFI board. Question is all of that even going to fix the problem? I don't know. And is it even worth the effort? Probably not. So I really think at this point what I need to do is I need to go grab a CRT and hook it up to this thing, because that's the way I'm going to be using this. I'm not going to be using it on the RetroTink once I actually get this thing all back together. So I need to grab a CRT. I'll grab the monitor I have up in my office upstairs, and we'll see how this actually performs with a real monitor. I want to see if we have the color fringing on the text in text mode. I want to see if that bar on the side really has an effect on the overall gain or brightness of the entire image. I just want to see how this thing performs. All right, here we have it. Actual CRT testing. Let's see what happens when we turn this on. Well, that's no color fringing if I've ever seen it. Disk drive is open, so we'll close that. Now we shouldn't have any color at all, because I didn't put the bodge wire back on to the 4066 on the corner of the motherboard. Oh, there is color though. I forgot that the default state of the 4066 when you leave the switch input floating is to pass the color signal through. Okay, so right now I'm holding it, I think, to 5 volts. And if I touch it to the ground pin on this socket here next to it, there we go. That's the switch input to the 4066, turning off and on the color burst. Now I'm noticing that I can just make out the bar on the side of the image. It's very faint, but the text and everything on the monitor looks absolutely perfect. So let me bring up the color bars. There we are. And no wonder why there's so much saturation. I had it turned way up. Yeah, unless you're a regular watcher of my channel, yeah, my 1702 here actually has on-screen displays, and it has a tuner built in. Yes, this has the guts of a TV inside of here, but it still has the S-Video input on the back and everything else. But I do have a remote control that I can control things. So all these settings are correct now, and that's good, because when I look at the colors that we're getting, this looks a lot more like I would expect. We have normal brown, orange, gray, pink. The green is good, yellow is good, aqua. That looks actually pretty good as well, and the magenta is very typical. Apple IIs don't have a really solid deep red. They have this magenta color. That's just the way it is. And again, if we reboot the system, it goes back to this menu. The text looks perfect. It's super sharp. I'm not really seeing any kind of like brightness issues or whatnot, even though we do have that line. I can just barely make it out. And even those interference patterns that I was seeing hooked up to the RetroTink, I don't see those either. I'm wondering if that interference problem was actually some kind of a ground loop issue. That maybe, yeah, I wonder if on this particular power supply, earth ground is also the same as the DC ground that goes to the computer. I don't know if that's the case with Apple II power supplies, but this monitor does not have a grounded plug, and that text, bright white, looks rock solid, no interference lines whatsoever. In fact, one way I can really test this is if I turn up the brightness, so I can now start to see what's in the background here. Hopefully you can see, and it's obvious that we don't have any interference patterns whatsoever. You can just see the line, but otherwise the video looks perfect. Absolutely perfect. The text is super clear, the brightness levels look correct, the colors look correct, and the color killer circuit is working properly as well. So that actually kind of tells me that I should probably take this 4066 out, just re-add the bodge on the bottom side that connects to 3 to 4, just like I had it before originally. And the transistor color killer that's on this board is actually working perfectly. It's just RetroTink doing those RetroTink things. I'm reluctant to put this thing back together, even though the case is ready to go and accept this thing, and then I can have a complete computer, because obviously it's got this random no start issue. I know this demo has been working fine, but I can tell you that I've had a bunch of times off camera where it definitely did the no start. Hopefully I've shown through this long 4-part series that when you have a machine stored in a hostile environment and combine that with the fact that this is a clone machine, which isn't well documented, and there were obviously a whole bunch of changes on here I had to kind of understand and undo, it really means you can get stuck with a whole litany of issues, and we certainly have had exactly that. Bad bus transceiver, bad trace, at least one bad trace. We had a bad CPU. We had a bad color circuit that was caused by the crystal oscillator being different than I expected. And then we had that whole additional circuit over here, which added a bunch of capacitors and did some other stuff. So I had to fix all that to get the hue to work properly. And now we have this random no start issue, which is almost certainly due to bad contact or another bad trace or something flaky going on. And for all I know, it could be a chip itself that's flaky, just like the original CPU that was flaky. Well, I thought this was the end of the video, but it's actually not. And you'll see that on the bench I have everything sort of strewn out, including the case and the computer that's actually running right now. And the reason why is because I thought I was going to end this video with this computer not working properly, meaning those random crashes. Well, what was happening is when I was testing off camera, I would push a key on the keyboard and it would just endlessly print a million of those keys. And really, really quickly, faster than the keyboard could even do it. And that implied that there's actually a problem on the motherboard, not with the keyboard. And if I push a different key, it would just endlessly print that key. It would switch to that key. Well, I apologize for doing this off camera, but I looked on the schematics and I wanted to figure out which keys are responsible for taking the key press that's in the latches that gets transferred from the keyboard over this ribbon cable into the motherboard. Well, it turned out that it was this chip and these 3 chips right here. And I think maybe those as well. I put little dots on them. Well, what I ended up doing is I started over here and I checked the pins, and if they were oxidized, I sanded them down, put deoxit. I think I might have done these 2 as well because I have those dots on there, but it still didn't fix the problem. It was still happening. So then I went over to here and there were one of these 3 chips that were responsible for selecting the keyboard circuit to basically copy what's in the latch into the data bus that would get picked up by the CPU. Well, one of these, I don't remember which one it was, when I sanded the legs with the little polishing bit, put deoxit in the socket, put it back in, well, the keyboard problem went away. So did the random crashing. So I'm thinking that it was one of these chips that are up in the upper region of the motherboard up here next to the ROMs that was responsible for A, the crashing, and B, this endless keyboard repeating problem that was happening. So that was a few days ago, and at this point, this thing is rock solid. And I know I had joked about this, taking every chip out and putting deoxit. I haven't done that. This is exactly how we left off after I had fixed the last problem. Well, or figured out that there was actually no problem with the interference and the color killer. That was a RetroTink problem. And yet this thing is now working perfectly. So what that means is that this thing is ready to go back into the case. I think I'm actually done. And yeah, I've left this running. I've left it running the dead test ROM here, which incidentally is actually booted off the disk version, and it's loaded into the language card, which I have plugged into slot 0. I left this running for something like 5 hours, and I manipulated the motherboard, moved it around, no problems, no freezes, no weird startup issues, nothing. This thing, it's just working. So I apologize for troubleshooting the keyboard problem off camera and fixing the computer, which ended up just being deoxit in one of those chips there, and well, polishing the legs. I don't know which one it was. Whatever it was, it's fixed now. So with all that said, I think it's now time for me just to, well, I'll just do a cut and I'm gonna put all of this stuff back in the case, and I think this thing is done. And here we have it. The MILMAR Apple II Plus clone is all back together. If you recall from the beginning of the series, this part is bent a little bit, bent down. I think something really heavy was sitting on this thing for a long time because the keyboard was bent. I've since fixed that, and I didn't know how to bend this back in a safe way. Obviously, I could try applying some heat to it, but I just didn't want to potentially melt it. And who knows, the whole thing's a little bit bent out of shape anyways. For instance, you might notice that this lid, even though it's all together and installed, is sitting kind of further down than it should. Part of that is most likely because the weight that was sitting on this, if the lid were on, would have been pushing that part of it down, and that's bent as well. Or maybe it was just like that since it was new. I don't really know. Another thing about this computer that doesn't look awesome compared to the real thing is the keyboard is set pretty deep in the case. Now it is mounted to the top cover, so it can't come any more forward this way. But I think the keycaps that they're just using on this are relatively low profile, and because of that, you just see quite a large gap around the edges. And take a look at the gaps and how homemade this all sort of looks. Like everything is sort of crooked a little bit and like it was cut out by hand. And
These keys are very close to the edge. They don't bind or anything like that, but they're super close. But if you go over to this side, there really isn't any room to move it this way because then the right arrow is going to hit. These keys have a little bit more space available to them, like the cut is kind of crooked. The whole thing's just a little bit crooked, but at least it does fully function. Everything works on this computer as far as I can tell. Now I will be keeping all of the parts and my little note with the problems and stuff inside of this computer, just so it's there in case I ever go to work on this in the future. Let's pop the lid off this. Original power supply is mounted, motherboard is mounted appropriately. All of the hold downs for the motherboard were gone, so I had to replace all of those. Pretty much most of the fasteners, or all the fasteners that hold the case together, they were all gone as well. Luckily, they're all, I think, M3, which is the same type of screw used on floppy disk drives, so I have loads of those. Don't have a lot of metric screws around the house, but I certainly have a lot of M3s. I did end up replacing the speaker because the speaker needs to sit over here, so you need to have a long cable. So I put a new one in. It's just sort of stuck down there. The magnet is holding it to the base. I didn't even use any adhesive. The computer is on right now. You might be able to see the little power LED that's lit up. What's funny is there is a power LED under the caps lock, and I didn't really touch that. I just left it where it was. It's sort of on its side, and it barely lights up the little window that's in here. I assume originally there would have been a different LED, or I'm not sure how it would have been to look a little bit better than this, but it is so dim, only in a dark room would you even be able to notice that this thing is on, at least from the keyboard. The case for the computer, it is bruised and battered. There's definitely some really shiny spots, at least in 3 corners, where I presume a monitor or maybe 2 disk drives and then a monitor were sitting on top. And then because this is bent down, there isn't a lot of clearance to put the lid in place between the chips that are on the keyboard and the case, but it does just fit. Everything on the back of the computer has been reinstalled, the video and the cassette interface, power supply with its pass-through. And if you recall back to part 1, the bottom panel on this machine, which is made of metal, was extremely rusty on both sides. So I ended up sanding it down as much as I could and then hitting it with rust converter. So I don't think it's going to get any worse. The finish isn't the best because you can see evidence of rust here and there. Obviously this would need like proper sandblasting and a full repainting if you were going to try to restore it. The goal for me was really just to stop the oxidation, not to mention if you touch this, if you pick the computer up, your hands aren't going to get dirty. Original badge is preserved, and I had to add new feet, new motherboard standoffs, new screws, new everything really to hold this thing together. And here's the final form of the MILMAR. 9-inch CRT, Franklin Ace 10 cloned floppy drive. Let's turn this on. Every time I turn it on, I'm not sure it's going to work, but it fired right up, looking good. Turn the brightness up a little bit. Apple II dead test ROM loader. So this loads it into a language card, and I do have a language card in here, but character set looks good. I mean, the computer really is operating normally. Awesome. One of the games that I used to play a lot of when we had an Apple II Plus as our family computer when I was a kid was this one, and it was Droll. And I'm pretty sure that we had this exact same cracked version here as what this is. It says here to call the safe house, 612-724-7066 BBS. Now, odd thing about this version of the game, and the same as the cracked version that I had for the 2 Plus, is it's not compatible with the 2E and the 2C. Not sure if it's something to do with the 65CO2 processor or what. So the whole idea is you have to shoot these guys, which is not easy. And then I got to get the little girl, which I already did, and then there was a little kind of a lizard looking thing down here. He's gone. Oh no. And of course with the Apple you can't push multiple keys at the same time. Oh, so you know, up, down. Oh, there, you got to get this one here. That finishes the level. It's a nice color game. Of course we're not seeing any color on this monochrome screen, but I am sure whoever was originally using this computer back in the day probably had a monochrome black and white television, because I don't think the color rendition would have worked anyways, although that's yet to be determined. Well, that is going to be it for the MILMAR Apple II Plus. I didn't think I would be done with this video. I honestly filmed an outro where I wasn't done because it still had the random crashing. But ever since fixing that keyboard problem, this machine has never skipped a beat since. Will it stay this way? I hope. The clone that I have in my office that I worked on back in, I think, 2003, which was similar messed up as this, hasn't ever skipped a beat ever since. And that's the machine I actually usually work on. If I'm going to be playing some Apple II games, I don't need double high res or a 2GS. I will use the clone Apple II Plus that's in my office. And you know what? Maybe I will replace that machine with the MILMAR now, even though this thing isn't as nice cosmetically as that one. It's still nice to see this thing up and running and, to be honest, saved, because who knows what happened to this thing between its life when Ricardo got it and sent it to me and when this was first used back in Brazil when this thing was new back in the 80s. Now, while working on machines like this, I always wonder if like the people who made this computer, because this was obviously made by people, this was not made by machinery, not in Brazil in the 80s. So what if those people who made this thing could see this video series and see that the machine that they worked on has been brought back to life in 2026 here in Portland, Oregon? And even beyond that, what about the person who used this computer and like put the wear on the case and the wear on the keyboard, who got this thing, was so excited to have an Apple II they could play games on and whatever productivity software that maybe they played with this thing? Because you can just tell by how worn the machine is. I think this thing got a lot of use over the years before it got replaced with something better, and then it was left to sort of rot away, which this machine definitely was rotting away. Anyhow, that's going to be it for this video series, at least for now, on the MILMAR Apple II Plus clone from Brazil. Whenever I work on machines like this that are just a hodgepodge of TTL logic, the TRCD Model 2 comes to mind. There's always so much for me to learn because there's always new and interesting faults that these machines can have. And yeah, this machine was no exception. There's nothing routine about working on machines like this because with that many TTL chips in there, there's just so many possibilities for problems and really interesting faults. And yeah, this machine certainly had all of them. So I hope you found it interesting. And if you did, I would really appreciate a thumbs up. But if you didn't, you know exactly what to do. Huge thanks to Ricardo for originally sending me this machine, and Vax11, a friend of mine, for packaging them up and actually sending them from the Midwest to me because Ricardo is on the East Coast. And I am looking forward to getting to the other Apple II machines that Ricardo sent in, the other clones that is. But I'm gonna have to take a little bit of a break now because I think people are totally sick of seeing me work on this thing right now. So I'll have to switch to something else, and believe me, I have tons of things to work on. And yeah, that's going to be that. So thanks to my supporters, thanks to my subscribers, I don't know, all the usual YouTube junk, comment down below, etc., etc. And that's going to be that. So stay healthy, stay safe, and I'll see you next time. Bye-bye.